Hey everybody. Today we're talking about the mean, variance, and standard deviation of discrete random variables. What we're doing here is measuring the center and spread of the distribution of those random variables. And we're using the same terminology and much the same formulas as we do when we're just talking about numerical data. So let's start with mean, also known as expected value. So suppose we have a bunch of different values, xi, of a discrete random variable x. So here the uppercase x is referring to the random variable, where the lowercase x is referring to the values. The mean is going to be the weighted sum of all the values. So take each of the values, weight them by their probabilities, and add up to get the expected value, to get the mean. For instance, here's a simple random variable x that can take on only 5 possible values, 60, 70, 80, 90, or 100. And I've listed the respective probabilities here in this table. To get the expected value, to get the mean, we are going to take each of those values, multiply by the probability, and add up all those results. So 60 times 0.22 plus 70 times 0.14, etc. Overall, I get 77.8. By the way, when I look at that formula, sigma xi p of x equals xi, I'm reading the sigma, at least in the context of college statistics, as just meaning add them all up. So that formula is saying add up all of the products of the xi times p of xi. Another thing we should note here is that 77.8, the expected value, is not actually a possible value of this random variable, which again can only take on the values 60, 70, 80, 90, or 100. The way to interpret the mean is to imagine doing the probability experiment many times, looking at all the results you get throughout all those different trials and taking the average of those. So the average of this random variable is 77.8. The expected value does represent the center of a probability distribution, much in the same way as the mean represents the center for a distribution of data. So here I've drawn a probability histogram for that same random variable. It takes on the values 60, 70, 80, 90, and 100 that I've drawn on the x-axis. And then the y-axis here is probabilities. The vertical bar that you're seeing here is the mean of this random variable, 77.8. And this represents the balance point of the probability histogram. So you imagine putting your finger under this plot at 77.8, the histogram should balance exactly. And that mirrors 100% the situation where you have a frequency histogram for data, where the mean of the distribution is the balance point of the frequency histogram. We measure the spread of a discrete random variable with variance and standard deviation. Typically, in college statistics, we focus more on standard deviation for reasons I'll talk about in just a minute. Basically, what we're doing here is we're taking each of the values that the random variable can take, subtracting off the expected value, squaring the results, multiplying by the probability of the value that we're looking at. We do that for every single value that the random variable could take, add all those up to get it to the variance, and then when we're done with that, we take the square root to get the standard deviation. Now, while that formula for standard deviation might be ugly, at least there's a pretty intuitive interpretation here. Roughly speaking, the standard deviation of a random variable x is the amount by which a randomly selected value will differ from the mean. For instance, using that same random variable, let's do the variance and the standard deviation. So for the variance, I take each of the values, like 60, subtract off the mean, 77.8, which we already found, square that difference and multiply by the probability. So when x is 60, the probability is 0.22. Do that for every single one of the values, add them all up, we get 145.2. That's the variance. Now, variance does measure spread. 145.2 measures the spread of the random variable x that we're looking at here, but it can feel pretty abstract. I don't quite know how to interpret 145.2 without more mathematical knowledge here. After we take the square root to get 12.1, we get a value that is more interpretable. Roughly speaking, if we do a random draw from this probability distribution, the value we get will differ from the mean of 77.8 by 12.1. Usually, most results from a discrete probability distribution fall within one standard deviation of the mean. So here I've drawn the same probability histogram that we saw a moment ago with the expected value as a solid vertical line. Then I've gone one standard deviation below the mean and one standard deviation above the mean and drawn dotted vertical lines. And so the idea is that most of the time when we run this probability experiment, we'll get a result in between those two dotted lines. Now, if you have a bell-shaped probability histogram, something that's looking a little bit more like a normal distribution, that proportion will in general be closer to 2/3. Now, both standard deviation and variance are measuring the variability or spread of a random variable, so why do we bother with both? Well, standard deviation has the same units as the random variable that you're looking at, and so it's easier to interpret, as we have seen a couple times in this video. By contrast, variance is harder to interpret. It's more abstract, and so we don't usually talk about it too much in the context of college statistics. However, if you go on in statistics, probability, data science, you end up working with variance a fair amount more. It's easier to work with mathematically, and it behaves more nicely. It just has some better mathematical properties that we don't really need to worry about at this level. Now, generally, we shouldn't do these calculations by hand. Even in the very simple examples that we looked at in this video, where we only had, 5 possible values for the random variable, the arithmetic got pretty unpleasant. Typically, we use technology. I'm going to show you how to do this using R, but honestly, if you're working with any other piece of statistical programming software or any other kind of app, the calculations are going to be pretty much identical to this. So what I'm doing is coding in the possible values of the random variable as a vector x, and then coding the corresponding probabilities as another vector p. And x and p both have the same order. So 0.22 corresponds to 60, 0.14 corresponds to 70, and so on. And then I compute the expected value, the mean, which I'm calling mu, using this code, sum of x times p. And I get 77.8, just as we did before. Notice that the code there, sum of x times p, exactly mirrors the formula for expected value that we saw a few slides ago, sigma x times p of x. Similarly, the code for the variance and standard deviation both mirror the formulas that we saw earlier. In particular, the standard deviation is square root of the sum of x minus mu quantity squared times p. The only thing you really have to watch out for here is the parentheses and the grouping, making sure that we take the difference between the x values and the expected value before we square, and that we multiply that times the probability before we take the sum, and finally, that we do all of that before we take the square root. Here we get a variance of 145.16, and a standard deviation, the square root of that, 12.05. Now, those last two values are very slightly different from what we saw earlier in the video, and that's just because R is doing a lot less rounding, being a bit more accurate than when I was doing things by hand earlier on and just using a hand calculator and rounding things myself.